to respond in the direct messaging, but we have to move on.
Okay.
Sam, are you ready to go?
Well, as ready as I'll ever be. Hello, everyone. My name is Sam Falvo, and I am going to just be giving a quick and dirty update of the ForthBox emulation environment that I've been working on. And part of that involves a new kind of subroutine threaded target compiler for it, which allows me to write and even port Forth code very, very fast. You hear things about retargetable C compilers, or Oberon, or some other systems, and they boast quite proudly, oh, it'll take a student several months to port this compiler. Well, I'm happy to report that my target compiler I initially estimated it takes days, but in practice it takes hours. So I'm quite happy about that. So let me go ahead and attempt to share my screen. Okay.
Screen is now visible.
Excellent, thank you. So basically, this is what the code looks like in the programming language. It is a dialect of Forth. It makes no attempt to be compliant with any established standards, although it does try to be as compatible as possible. Some of the things that you'll notice here are, for example, this T colon, obviously meaning it's a colon definition for the target. From what you can see here, it looks fairly like normal Forth code. Likewise, up over here, this is a fairly complicated, well, I wouldn't say complicated, typical. It's a fairly typical begin while loop in Forth. But then you'll see something over here, this TX colon. What is that? Well, I'll explain that in a little bit. But basically, there are words that Forth allows, which are not syntactically correct in an assembly language listing. And so what you need to do is create an alias for these words that is assembly compatible. And the X variance, or the TX colon, allows you to do that. So in this case, drop 2 is syntactically compatible, whereas 2 drop generally is not. So I'll explain this block up here in a bit. For now, let me just show you what the result is when I pass it through the compiler. And you'll notice that it is legitimately an assembly language listing. Like, you still have to use an assembler and or a linker to work with it. And so here you'll notice the entry underscore drop 2, which of course calls drop twice. And you'll notice that there is no definition of drop in the source listing. And that is a very deliberate design decision. I think that is the key for what makes this system preferable in my opinion, because it allows you to just focus on the application that you're trying to write and not have to worry about the primitives that you're dealing with. And so, entry init, entry type, etc. And of course, as you can see here, it is subroutine threaded, hence all the jump subroutine instructions. And finally, entry put B. You'll notice that string literals are embedded right within the code. So we have this jump subroutine that I underscore string, which this subroutine is responsible for doing whatever stack manipulation is necessary to push that string onto the stack. And then it just returns directly after the string, which in this case we just type and continue forward. So how do we work with that? Well, if we go back to our main code here, for example, like CStore and CFetch, and all these other low-level primitives, we have to tell the compiler that they exist somehow without actually giving a definition. And that's what this xref and xname does. The xref construct here basically says that there is a subroutine defined somewhere elsewhere called entry underscore dupe in this case, or entry underscore over, or entry underscore swap, right? You can list as many words as will fit on a line here. But then there are other definitions such as CStore and CFetch, which again do not have valid representation in an assembly language listing. So you have to give them an alternative name. In this case, CHRSTO for character store, for example, or INCR for increment. And those you have to write yourself. And that's where this bootstrapped assembly language listing comes from. And for example, here's the definition that I wrote for I underscore string. There is a comparable definition for numeric literals as well. And what you can see here, let me exit that and let me actually edit this. And what you can see here is basically with these lines, we manipulate the data stack pointer. We do our address calculations. We push the, or in this case, we actually store the string length directly onto the stack. Here we're pointing a temporary register directly at the string so that we can calculate our addresses, calculate our new return address, push it back onto the stack, and then return, right? So this is all black magic. You only have to write this once. And once it's defined, you can use it as many times as you want, obviously, for as many strings as exists within your program code. Here's our character store, character fetch definitions. And everyone will recognize character dupe. Basically adjust the stack pointer, fetch the old value, and store it in the memory, right? So this is nothing new. I think the only real innovation here is basically having an environment where it's not, where you can compile forth without having the basic primitives in place. You're just promising the compiler, you know what, hang on, proceed without the definition. Trust me, I've got the definition in another source file, right? So once you have that, what you can do, if I look in the build file here, what you're going to see is I invoke the target compiler here with this Shoehorn invocation, and I use that to generate an assembly language file. And then I pass that indirectly to the assembler by way of this bootstrap file, right? And that will generate our binary. So if we look at the bottom here of our bootstrap file, I've got this pound include the actual output of the Shoehorn compiler. Obviously, if your assembler works differently, like if you take modules and it generates relocatable object modules, use whatever is appropriate for your assembler. I'm just saying that this is how this works for this particular assembler. And then finally, when we're done, I actually embed the resulting binary directly into the boot image of the emulated environment. So if I wanted to invoke this, I would say, you know, K1 emulator. So we now load and execute. We're actually running inside our IMF environment. I gave a presentation of IMF the last time here. And if we take a look at address 9000, you know, this is all the binary code that goes into making up that Hello World application. So if I display our registers, if I tell the program counter to start at the base address there, and I tell it to go. Hello world from Shoehorn, right? So this is actual Forth code, which is compiled to assembly. We assemble that, and then we actually execute it from within this binary environment. You'll notice that there's this little A at the beginning here. That's just a debugging aid that I forgot to remove, so don't worry about that. But the actual core of the Forth code is actually what printed out that message there. And then I realized, you know, since we have this Valentine's Day challenge, why don't I take this and I actually make this make a little graphical demo. And so that's what I did here. As you can see, I've got a significantly larger number of primitives that I'm depending on in order to execute this demo. I also have some variables that I've allocated manually in RAM. But then I also have this, well, I call it a cosine lookup table for convenience, but it's actually cosine squared. But basically, this is a table with pre-computed offsets on the screen that follows a cosine squared waveform. Then I've got basically a little driver here that works with the emulated disk, quote unquote, interface on the emulator. And I use that to load assets, graphics assets. The first of this chunk of code here loads the entire background screen. And then this chunk of code loads the actual heart sprite. And so here's the basic graphics engine. And what it does is it basically just draws the heart from left to right and right to left, and adjusting its vertical height based on that information. And there's the main loop of the program, right? So this is, as you can see here, this is not a toy program. Like, this is a legit, honest to goodness Forth program. And if we look at the resulting the resulting assembly language code, yeah, I mean, there's a lot of stuff that's going on here, right? I mean, too much for me to actually list in this particular demonstration. But what I can do, again, is I can run it. And if I bring this over here, apologies for the flickering, but you can see that it is actually updating the bitmap screen with the heart logo, and it is doing honest to goodness work, right? So as simple as this compiler is, it's definitely not a toy. I see that Ting's hand is waving there. Ting, did you have a question? I guess not. Okay. Well, let's.
Yeah,
let me go ahead.
I have a question.
Sure. Go ahead.
Yeah, I'd like to understand how you handle immediate work when you do this, when you compile, if you are not working in the target.
I'm not sure I heard that correctly. Are you talking about the bitmap images?
No, the immediate work. When you are compiling, and if you encounter an immediate word, how can you execute it?
I'm still not hearing the question correctly. Like how am I actually kicking off the environment? Oh, immediate words. Immediate words are handled. Let me actually get out of this demo and into the Shoehorn compiler itself. So immediate words are handled in the Shoehorn compiler itself. So if I go into its compiler, basically I've got a bunch of support words here But if you define any word with a CMP colon prefix, that will allow you to add new immediate words. So here's the definition for ahead, if, then, and the more conventional fourth control flow words. I also have the definition up here for semicolon for exiting out of the colon compiler. And I think this is the first one, yeah. So this is the first immediate word that I defined here. And then everything else pretty much follows the same basic pattern. Let's see here. I have a question on chat asking how long it takes to port to a new processor. 16-bit MISC, I've not tried that, but I have done 64-bit RISC-V. So here is the entire source code for the RISC-V 64-bit backend. That's it, everything. And so what I can do is, instead of changing from 65816 code, I could actually, if I change this to, it's not easy to use in the sense that 64.fast, but it is fast to use, I suppose. So if I come back into if I do shoehorn sh.hello.f, let's see if this one, oh, nope, hang on. So now, if I do, and so now as you can see, all the code's in 64-bit RISC-V. And that rv64.fs file, it took me about an hour to 2 hours to write and debug that. So basically, I can retarget this compiler in a matter of, I conservatively say days, because you've also you also have to concern yourself with like the application binary interface and whatever system bring up and tear down requirements your environment has. But in terms of actual porting the code and actually generating new code for a new platform, it can be done in as little as a couple of hours.
Do you have much more of your main presentation, Sam?
Nope, that's it. I wanted to show you the Hello World example and the Heart demo, and basically just give a quick tour of the code. I think I've done all that.
That was way cool. So any more